there, Internet students. It's Mr. Hermanson again. Today we're going to talk about chords and arcs. A chord is a line segment that has endpoints on the circle, like you can see there. And an arc is the corresponding part of the curve of that circle that is defined by that chord. All right, so go ahead and think about this first question. See what you come up with. All right, here's what I was thinking, that they're the same, so EF must be equal to 15. And there's something to be learned there, that if you have the same length of a chord on two congruent circles, then the corresponding arcs are the same and the angles are the same. And so our first theorem here is within a circle or congruent circles, congruent central angles have congruent arcs. So if these angles are the same, then these arcs must be the same. Okay. Also, congruent central angles have congruent chords. So if these are the same, then these line segments are the same. And also, congruent chords have congruent arcs. So if AB is the same as CD, then this arc here will equal this arc here. All right, so looking at this first picture, what can we conclude if VT, so if that is congruent, let's mark it like that, to RP, what can you conclude? You can conclude a lot. You can conclude that arc RP will be congruent to arc VT. Here's how we show arc. We know that these angles will be the same. So angle VDT will be congruent to angle RDP. All right. Why don't you try one? Well, since this is an isosceles triangle, that means that this angle must be the same as the side opposite. Same with this. So we have like angle, angle, side, which tells me that the two triangles are congruent, so then angle O must be congruent to angle P. And then with that, you get that the arc BC is congruent to arc EF. And also that the chord BC is equal to the chord DF, congruent. All right. Theorem 12.7, within a circle, chords that are equidistant from the center are going to be congruent. And the converse of that is also true, that if chords are equal in length, then they are the same distance from the center. Now, the distance is defined by a line that's perpendicular to the chord. Okay, here's a proof if you want to check that out. So what that's telling us is that A, since those would be congruent triangles there, A must be the same as the other side, which is 6. And since these are equal in length, 6 plus 6 has to equal 12. So A is 6. All right. So what do you think the value of X is here? All right, moving on. Another theorem, if the diameter is perpendicular to the chord, then it bisects the chord at its arc. So so what we're saying is that both sides of this are the same. That seems kind of obvious to me since these would both be radius, and since they're both right angles, those are two congruent triangles. Anyway, so we can use that. And then some different ways to look at it. If AB is the diameter and CE is congruent to ED, then that tells you that you're on the line that's perpendicular. And if AB is the perpendicular bisector of a chord, then AB is the diameter, or it contains the center. Okay. So given an arc below like the one, how can you find the center of the circle that contains the arc? So here's what I'm thinking. Draw yourself a chord and then bisect that chord. So draw the perpendicular bisector of that chord. So I'll make little marks here to show that I did that. Let me draw this next one in red. So what if I did that again? Let's say I picked two new points, drew in the chord, drew in the perpendicular bisector of that chord. So with a compass we could do this, but we're not going to use compass online. And since those are both diameters, the one point that they should have in common is the center. All right, go ahead and do this. Got it? See if you got it. All right, so I'm just going to go through that, and I'm not going to really measure that, but let's say we draw one chord, draw the perpendicular bisector, draw another chord, draw its perpendicular bisector, and where those two perpendicular bisectors meet is the center, and then you can measure the radius from that. All right. So let's go ahead and find the missing length here. So we know that that this is a perpendicular bisector right here. That means this side is 6. So we can go ahead and do the square root of 5 squared plus 6 squared. And that would be the square root of 61. If we want to leave it in simplest radical form, we'll do that. If we want to approximate it, it would be like 7.8 maybe. All right. Go ahead, you try, see if you can figure out circle B here. All right, that's what I got on that one. Hope you agree. All right, why don't you try one more here? That's what I got. All right, this looks like we're on to the practice. Good luck with that. We'll talk to you soon.